Before we dive into this tutorial and start building our setup, let me just quickly mention that this goes back to an idea that Simon Fiedler had. Very talented Houdini artist, so thanks so much, and I'll just borrow heavily from his setup. Let's get going. So now that we have our farm running, let's try something a bit more elaborate and actually run a sim on this. And what you see here is kind of a foamy behavior mimicking a polyurethane foam that maybe forms the sole of a shoe or anything you like. And this is a combination of pop fluids and grains, which can be efficiently distributed across the farm using PDG, for example. So let's build that. Let's start out with a collider, and for now we're just going to use a torus because I am darn lazy when it comes to modeling. You could also use a 3D scan of any product that you want to fill with this. I'll just go with a torus and increase the rows to 24 and the columns to 48. Make this a bit more higher res, and also move this up a bit. Then attach a null, call this one out_collider, wire this in here, and then for rendering just attach a clip, which I'll wire in 2, highlight, and I'll just keep the primitives below the plane, and then dial in a distance to my liking, like that. Next, let's build our particle system by creating another geonode here. Maybe let's call this one sim for simulation, and let's call the torus collider instead. Then dive into the sim geonode here. And the first thing I need is an emitter, so I'll go with a simple sphere here, leave that set as is, just dial back the uniform scale to 0.1 like this, and maybe move this one to 1 along the x-axis. Then I'll attach a transform, and I just want to have this thing rotate, so I'll drop in a short expression, $ff, that's the current frame, times 0.75, highlight this, check my real-time toggle and hit play, and I can see I've got this rotating emitter here. It's good. Let's just save this for now, and maybe let's decrease the sphere size a tiny bit more, like this, 0.05. That looks better. Just for completeness sake, I'm not sure if I'm going to use it. Let's attach a null here, call this one out_surface, and then let's just directly drop down a pop net, where we'll wire in the out surface into the first slot, and then highlight this, dive in there. So that's your standard setup for a usual new pop net, and what we'll do here is slightly modify it. So first thing we want to do is add some gravity to it, just a gravity force, which I'll wire in down here, and then adding a collider. So basically I'll need to merge in a static object, and just going to drop down the static object too, and in here I just want to point my subpath to my collider geo thing that we called out_collider. Wire this in the merge, and then just check that my wires are set up like this. The final thing what I need to do in here is add a pop fluid, so I want this to behave fluid-like. I use a pop fluid node here, new node since 17.0, really great thing. So let's dial in those settings here. I just want to decrease my particle separation to 0.02. Then in my pop solver I want to increase my minimum and maximum substeps to 2, so we're running a bit more iterations here. And let's just check our pop source. So we want to scatter our particles onto our surface, and then under birth I want to have a constant birth rate of say 12,000 particles. Life expectancy of 100 is good, and we can leave the rest as is. So let's just head into our static object and let's uncheck display geometry and just play the simulation and see where we end up. Well, that is not too convincing, because in the static object, under the collisions tab, let's scroll down here where we see the collisions guide, and what I want to do is on the one hand I want to increase my uniform subdivisions to 60, and also when scrolling down further I want to invert the sign so we are getting the kind of collision normals to point in the right direction. Let's uncheck the collision guide and hit play again. And now we're getting something more akin to what I expected. So this fluid-like behavior of those fluid particles just flowing into this torus shape here. That's what we want. So let's head back up, attach another null here, just to be able to easily reconfigure this if we need it later. And then in the pop net, let's just select our only pop object, so we're only accessing those particles that we just generated in there like this. So what I want to do now is select kind of the outer area of this particle fluid, just the outer borders, and that's where I want to emit my kind of foamy, bubbly particles, so that the foam kind of emerges at the edges, at the borders of this fluid, and not in the center, because that would need too many iterations to push out all those spheres to the outside of my simulation. And for that, I want to only regard particles which have hit the collision geometry. So for now, let's just briefly dive back into the pop net, just middle mouse on this. And in the pop solver, let's go to collision behavior and check add hit attributes. Then let's dial down these attributes here and uncheck everything except the hit number attribute like this. So we'll now have an attribute on each particle, on each point, that tells me how many times this particle has hit some collider, which is exactly what we want. So back up and let's drop down a point triangle, wire our null in here, and I want to check if the hit number, which is stored under the attribute called hitNum, is smaller than 1, so if the particle hasn't hit anything yet. And then we want to remove the particle just using the remove point function like this. First geostream particle with the current point number like this. And also we want to set our initial p-scale here. So just f at p-scale equals to 0.005. Really small for now, like this. Let's just highlight this and check and resimulate that. So yeah, now we're only getting particles that have hit something already, in this case our collider geo here. Now if we middle mouse on this, there are lots of attributes that we now don't need anymore. So let's delete them using an attrib delete, wiring this in here, and deleting all point attributes. Middle mouse again, they are now gone. Next, let's attach another point wrangle, and then we want to find out how many neighbors each point has. And I want to use this neighbor count to determine if a point is more at the edge, where it has less neighbors, or if it's in the center of this fluid, and then want to get rid of those points in the center. So basically what I'm doing here is first finding out all the neighbors of each point, using the nearPoints function, which returns me an integer array, like this. Want to look on our first input slot from the current point position, within a radius of, say, 0.05, let's find a maximum of 96 points like this. And then let's actually find out how many points we found, checking the length of this array here. So let's call this maybe np for number of points, and it's equal to the length of this array. So len npt like this. And now we want to check if our np, that means our length, is above a certain threshold that's used for this case 72. And if it is so, let's remove our current point. Like this. That didn't do much. Let me check again. Yeah, so what I want to do first is back in our PopNet, dial in some different collision behavior settings here in our static object under the physical tab. Let's just decrease the friction to 0 and the dynamic friction scale to 0 too, like this. Again, let's resimulate this and then heading back to our point wrangle, this time deleting everything that's not colliding like this, which still doesn't look as promising as I'd like to, so let me head back into the PopNet, and in the pop object under the physical tab, let's dial in those parameters here as well. So I want to have 0 bounce forward, 0.5 general bounce, and again, let's keep our fingers crossed and resimulate that. So yeah, looks more promising, and yeah, now I'm getting the behavior that I expected. So as you can see, all those values here, like the number of neighboring points, depend heavily on your simulation parameters. And I think that's what I dialed in my original setup. So yeah, what we're getting here now is exactly that border I've been looking for in that fluid simulation. Before we build the grains part of the setup, I want to also take this whole fluid simulation that we have, including all those particles, and just use them as is. However, first what I'll do is just drop down another point wrangle, wire in my fluids here, and then give those a random p-scale value. Just using our random function with the ID attribute for each particle, and then just fitting this between 0.5 and 1.0, and then finally multiplying this by 0.01. And if you want to check on these particle radii, let's use the sprite node, wire this in here, but before we do wire it in here, let's just change the sprite map to $HFS Houdini Pig Sphere Mat Pig. So that's your standard default grain sphere here, like that. So that for some reason clearly didn't work, and that's because in the point wrangle I misspelled p-scale, so instead of p-scale, let's set it to p-scale, and now we can see we are getting correct sizes for these individual points here. Let's try wiring those other ones here. That works too. Okay, now it's finally time to set up our grains, again using another PopNet with these borders of our fluid simulation in the first slot and the general overall fluid simulation in the second slot like this. Let's highlight this and dive in there again. So nothing too special yet. Got our pop source, which we'll set up to use the points and not scatter on the surface. And then in the birth tab, let's set the constant birth rate to 20,000. Just for good measure, not sure if I'll need it when building this setup, but let's just add a new particle group called newpart. Let's dial back the life expectancy to say 20. Let's set an initial velocity of 0 for now, so 0 variance on that. Stream and bindings are fine, like this. Next, as we want this to be grains, so individual particles that can push each other apart, let's drop down a pop grains in here, just in between here. And in here, let's set this up. So what's going to happen later is that we are really spawning lots and lots of particles in here, and they will grow over time. So they will try to push each other away and apart. And the more particles we have in here, the more constraint iterations we need for that. So for the beginning, for checking this out, a constraint iteration of 20 or 200 is fine. However, in the end, what we want to do, especially before sending this off to be distributed on the farm, is really increase those to 4 or maybe 8,000 iterations. For now, that's fine. let's just dial in the friction. With colliders, that's fine. Just with particles, let's dial it back a bit to 0.1, uncheck accurate friction, and let me just scroll down here and check. Yeah, that looks about right. Now in the Solvers tab, I want to set my velocity blend to something really, really low. So what velocity blend does is it takes the velocity that the particle already has and blends it in with the next simulation step. And I want to avoid that. I want to have my particles feel kind of sticky and only be moved around by them each other, pushing them apart. So let's set this to something really low, like 0.05, and that should be it in the Solver tab. Next, for this simulation, we'll need a bit of drag to slow those particles down additionally. So let's just wire in a pop drag in here and set its air resistance to 0.25. And all those values came from lots of trying out and trial and error and just trying to dial in those settings until they looked right. So 0.25 should work here. Let's, on the pop object, just check. Collision tolerance looks fine, and let's just check physical attributes. Yeah, that looks fine for now too. Now what I want those particles to do is grow over time, like expanding foam and pushing each other apart. So what I need to animate their size, their p-scale over life, and I will do that using a pop wrangle, which I'll wire in the middle slot in here, just for good measure. Add a merge for later. And in the pop wrangle, what I want to do is first I want to create a value that tells me how old a particle is, ranging between 0 and 1. Let's call this one just U for now, and I'll calculate it by dividing the age by the particle's maximum lifetime. Like this, that's all there is to it. And then I will refit that, in my case call it S for maybe scale. So I'll take my U and assume that it ranges from 0.0 to 0.1. So basically what I'm doing here is I'm scaling this up to be between in the range from 0 to 1, just in its first 10% of its life, basically. And then finally what I want to do is, of course, drive this with a ramp to be able to dial in the behavior a bit more precisely and art-directed. So let's drop down the final p-scale, which will be a ramp of S, and then let's dial in the overall size with another float, call this one amp for amplitude, and finally add a bit of randomness by using a random function, again using the particle's ID, and let's fit that one to be between 0.25 and 1, like this. Let's create all those user interface sliders, and of course we get an error here. It's because we have a few points and commas too few / too many. But now we have this amp slider here, which we're going to set to 0.02, which is our overall size, our maximum point size. And then here in the ramp, let's just set those individual nodes to B-spline and then dial in, well, something like this. So this will be the size of our particles over their life. I think we're almost good to go. Let's just add to this a bit of gravity and of course the colliders. So first, let me just drag this down, add some gravity, just a tiny bit, so minus 0.1, and then merge in colliders. And I think we're gonna have 2 colliders here. So let's add in 2 static objects, wire those in the merge, and then resort my connections like this. So my first static object will be our overall collider, the out collider here, that thing. And under collisions, let's on the one hand make sure we increase the uniform divisions and then again invert the sign. So our collision normals point inwards, and also we don't want to display the geometry for now. Let's also reset this thing. And in the second static object, let's just set this subpath to backtake op input path point and 1. So this will point to our first input slot. And I don't want to display this geometry either, and the rest of the settings we'll just leave it as is. One final thing, let's just check the pop solver here. That's all good. That too, collision behavior is fine. Yeah, that's all good. Okay, let's head up one level. Again, save this, and maybe before we pipe this into Sprite, let's attach a null. Call this one out underscore grains, like this. So that goes in here, and finally into the Sprite. And this popnet, of course, I only, again, want to access the pop object, like that. Okay, let's save this, keep our fingers crossed, and hit play. We can see now we created this grain foam simulation of expanding foam that's kind of being generated here at the edges of our previous fluid simulation. Let's reset this and save it. And this is really simulating really quickly, and you can see that later in the simulation we are getting quite some intersections between the grains. So what I want to do now as I'm preparing this for PDG is I want to increase the substeps in our grains, so that's the constraint iterations. I want to set that to a really high value. Let's try 4096 for now. Again, head up to our normal OBJ level, save this, and let's start building our PDG net. So again, I'm going to drop down a top network here and dive in there. So my goal for this whole thing is to be able to simulate it distributed on a farm. And the easiest way of setting that up I found is using the shelf tools. I hate to admit it, but in this case they are really, really great. So what I want to do is, with my topnet down here, my collider and my sim, I want to go into my sim and into my actual popnet where I had the grain simulation running. And let's just skip ahead a few frames where there are actually some particles like this. So with my PopNet highlighted here, I'll just head over to the Grains tab, and in here I'll drop down 2 of those slices. So click on the slice first, then select our grains here and hit enter. And what that does is within my PopNet, it drops down this slice plane node here. Let's dive up again and do that a second time, again clicking on slice and then on our grains hitting enter. So now I've got those 2 slice planes here. And slicing this thing twice in that same direction doesn't make sense. So let's set up the second slice plane in the Z direction like that. So now I've got 4 slices. Again, head up 1 level and now click on the distribute particle fluid. Select the grains here and hit enter. And now Houdini is automatically asking me which distribution method I'd like. And I set this up for slices, so I'll just click slicing here. And that not only created a bunch of nodes in my PopNet, but also in my out network, it created this HQ simulation driver, distributed sim, which is nice, but we won't be using it because we'll be using PDG for that. So let's just either bypass this or delete this. So back to our OBJ level and into our sim and into the PopNet here. And see, we added a few control nodes like this distributed pop object and this distributed pop object controls. And of course my 2 slice planes here. Also, when heading up again to our OBJ level, we can see we added this distributed underscore pop object here, which is there to, on the one hand, access and then save those individual slices, and also a file load which will load back those slices. And you can see there's this variable here called $slice, which the whole setup is accessing and relying on to actually address those slices. And also this file merge will take care of actually merging and reassembling those individual slices of our simulation to just hand me back one single simulation. So in here, I'd like to attach a null to this slice geometry node here. So drop down a null, wire this in here, and call it out underscore distr for distributed, and then sim for simulation. Or let's call it slices, like that. And this is the actual node that I'll reference in my topnet. So let's do that. Go into the topnet here, and let's drop down a rob geo node here. So the path I'll be linking and referencing here will be this very node that I just showed you. So in the distributed popnet here, the out distr slices. Then the output file path, let's change that a bit so that we'll actually be referencing the individual slice. And for that, we can head over to our distributed pop object here, and in the load slices, let's just steal this expression here, copy it over to our topnet, and then paste it in here. Let's just drag this down a bit, and under the rob fetch tab, what I want to do to enable all of this magic is check distributed sim and then increase the slice counts to 4 as we have 4 slices. And also I want to point this to our control DOP. That's the DOP node that's been created by our shelf tool. So let's do that by heading over to our sim geometry, then into our second popnet here. And here we have our distribute pop object control. So let's accept that. And we have it linked up now. Let's save this. And the last thing I have to do for now is exchange this local scheduler here with an HQ scheduler to be able to run this on my farm. So let's delete that one, drop down an HQ scheduler like this and set it up. So my working directory, that's fine like that. My HQ server will be set to 192.168.1.161. That's my main server here. And let's just check override local shared root here and load from HQ so I can check my paths. That looks about right. Finally, my universal HFS, let's just set that to my local Houdini install. That's the directory where Houdini is installed on all of my clients too. Let's save this, and finally in the rob geometry under schedulers, let's just highlight the HQ scheduler here. It should not be necessary, but just to be sure. Let's save this, reset this, keep our fingers crossed, highlight this node and hit Shift and V. Send it on the farm and see what happens. So until now, that's looking good. And let's check in our browser. We can see that on our HQ server here, we got one job running with 4 clients assigned. So let's click that and that one here. And we can see we've got those clients running. So let's maybe head into our remote desktop application and check the individual machines. So let's maybe check Nutcracker7, who's working on this job. Yeah, and we can see, apart from this nag screen here, that our CPU is doing something and the farm is actually calculating. So let's minimize this and head back into Houdini. And we can see this is simulating pretty okay currently. So what we could do later is increase the grain density, the particle count, and maybe the constraint iterations on the grains. But for now, let's leave this running. So now, as this is nearing completion, let's head up and go to the distributed pop object here, dive in there, and in the load slices, let's see if that actually works and what we simulate so far. So yeah, we can see the simulation results, the grains coming in here. So let's attach to that, again, a sprite sub, and we're just going to use that one out of the sim here. So let's just copy this one here and back to the distributed pop object here, paste that, wire this up and highlight it. And we can see these are our simulated grains running out of our farm. Let's maybe disable the display flag on our sim. So when we dive in here, we only load back our geo without running the actual simulation. And we can see that is looking pretty neat so far. So this is how you set up a basic grain simulation to be distributed using TOPS and PDG running on the farm. Now, when it comes to rendering, what I want to do in this case is use a third-party render engine, in my case Redshift. And how that is done and how that can leverage the power of PDG and my HQ farm, well, that's the topic for our next tutorial.